Exercise 41.2. The exercise is to be solved with the assistance of the TI-Nspire CX CAS version 3.2. Consider the region bounded by the graphs of y equals x squared minus 7 halves x plus 23 eighths and x plus 2y equals 8. Part A. Provide a graph of the region. B. Provide a graphic approximation of the area of the region. C. Provide a calculus calculation which yields a decimal approximation, 5 significant digits, of the area of the region. D. Assess the correctness of parts B and C by examining for consistency between the two results. E. If able, obtain an exact value for the area of the region. Okay, let's get started. Since this question involves both decimal approximation answers and exact answers, we might do well to think about our calculation mode for the calculator. To do that, you can go here to the document key, settings and status, document settings. Let's see what we have here. Alright, my Nspire presently has a calculation mode of auto. What's auto mean? Auto means that if there are no decimal point number inputs, it will provide an exact answer, unless the exact answer is inconcise, in which case it will then resort to a decimal approximation. If there are decimal number inputs, it will provide decimal number results. Okay, that's the auto mode. Now there are the two other choices here, exact and approximate. Exact and approximate are sort of the extremes in each direction. If you choose the exact mode here, alright, now everything is an attempt to be exact, and that may sound good, except when you start to realize that every single decimal number will be recorded as a proper rational fraction, which can actually get rather clumsy for many of your calculations. So that's probably not such a great idea for us, certainly in this situation. And the approximate calculation mode, alright, well now everything is recorded as a decimal number approximation, which starts off okay for us, but again, when we encounter our exact requirements later on in the question, we're going to have to change the mode, and no need to do that. We should just simply pick this nice auto mode to begin with. In fact, for really most of your general math work for maybe the first 1 or 2 years in college, auto mode is probably your best choice as a default. Also, in our particular case, you may notice our question involves two equations, and if you look at all the coefficients in these equations, you'll notice you're seeing there's no decimal numbers, so the auto mode here works real well for us. It will try to get exact results if they're concise when that moment arrives. Now this exact result, this means when we have the calculator application running. When you're in the graph application, that tends to be a decimal number situation all the time, although you can force certain exact results in some cases, but mostly it's all about decimal numbers when you're in the graph application. Okay, a second item here I suppose that we might tinker with, since we do happen to see that this question is requiring 5 significant digits. Alright, since that's the case, we might as well change our display digits to 5, so that'll be fairly easy to work with when the time comes. And keep in mind, this display digits we see here is for the calculator or spreadsheet mode. The graphs has its own display digits menu that we can work on later on at that time. Okay, we'll click OK. For the first page of the document, I think it might be best to make it a notes page where I could record the summary of everything right here, and then all the other pages can be support references. So here, for instance, we could have exercise 41.2 solution summary. Here we could have part A and say that a graph of the region is on page 2. Now, since this is a sort of a summary page here, let me make this title line here bold font. And let me move it to the center there. Okay. Now, let's go ahead and create page 2, which should be a graph. Entry line prompt is awaiting us, and let's take that first function, and that is the y equals 2x squared minus 7 half x plus 23/8. Should be a parabola. Okay, it is. And let's hit tab, bring up the entry line again, and this time, well, let's just solve this linear equation for y mentally, and that would give us a y equals to the quantity 8 minus x, all divided by 2. Okay. Should be a straight line. Okay, we have that. Now, the bounded region is right here in sight already. Let's just make this graph look nice, and I like to bring the region front and center, enlarge it as much as I can. And so I think I'll go here to the menu, window zooming, and maybe a zoom box. First corner, say about there. Second corner out. I'll go out here a ways so that I have some room to also record function labels. So I have this. Escape, put that tool away. If I can, I like to have no distortions in my graph. In other words, if a circle was to be sketched, I would like it to look like a circle. And to achieve that, I need to square the axes. So let me try doing that, see if it still looks okay. This is something I don't always do, but if it works, it looks nice. Okay, squaring axes still keeps things in pretty good order. So I'll keep that basic idea. Although right now the axes are very densely scaled, I would like to try to fix it up to make that look a little more readable. And I'm looking at the x-axis right now. It's about 11 units long or so, and the y-axis is about 6-7 units long or so. Okay, looks like I can afford to go to a 9:6 x-axis to y-axis. I like to keep a 3:2 ratio so that I keep the axis scale the same, and I also want to try to make this look simpler. So let's go back here. I'll go to the window settings. Alright, X min. Let's just make that a -1. Tab. X max. I'll just make that an 8. The scaling, just 1 apiece. Y min, a -1. Y max, a 5. And scale that at 1 apiece also. Alright, I think that will look much nicer. Okay, this looks pretty good. Let's move these labels a bit. This can be F1, this can be F2. Alright, starting to look a lot nicer. Now I see the bounded region, but I want it to be very prominent, like shaded. And as far as shading goes, if you did this like turning these things into inequalities and shaded above or whatever, that would sort of do it, but you'd have a lot of colors all over the place that you don't want. To shade a specific region with the Nspire, I find it's easiest to simply sketch some polygon that basically approximates the region and fill it in. Also, the advantage of this in this case is that I can use the polygon as a source of graphic approximation as well. So this actually turns out to be a very efficient idea for me, I think. So let's start that. I'll go to the menu and geometry and shapes and polygon. Alright. One point there. Point there. As long as I still have a pretty good approximation of the curve, I'm willing to keep going. As it starts to take a sharp corner, I need more and more points to avoid introducing error. Okay, there's the polygon. Escape, put that polygon tool away. Now I will take the polygon and decide to pick a fill color of, let's say, yellow. Alright. Now at this point I want the graph of the region to not have all these polygonal lines and dots and everything. However, I actually also want to eventually use this polygon. So what I do here is I'm going to actually copy and paste this whole page so that I have a page 3 with the polygonal approximation ready to go, and I'll continue on this page 2, turning into a nice looking graph of the region. In other words, control, let's look at the entire document and go here, copy and paste. Alright, this page 2 is going to be the graph of the region, so here's what I will continue to work with this. Now, first of all, this polygon, now I want to also color that line yellow as well. Okay, it's looking better. All these points are kind of distracting. Let me hide them. Alright, let's see. Looking better. I want to be very clear about what the bounded region is, so let me put a little bit of text labeling here. Bounded and region. Okay, move this more central. Alright, looking really pretty good here. The only thing maybe adding to this graph would be these points of intersection here are worth at least approximating here right on this graph. So let's do that. A couple ways you can do that. Here's one way, and that's to go to the menu and geometry and points and lines and pick intersection points, and we'll pick graph 2 as one of the graphs. Pick graph blue here as another, and we have this. Now that's quite a bit of decimals appearing on my graph here, and for the graph I don't want it to maybe have quite so many decimals here, make it look a little nicer. So what I will do is, let me escape, put that tool away, go to menu, go to settings. Since I seem to have my coordinates all between -1 and 9, I suppose I can do plenty well with just floating 3 decimals for everything I put on this graph here. Okay, so these look a little simpler. Let me just move them so they're not obstructed or obstructing. Okay, I think that is a pretty good complete graph of the region. Now, let's go on to the part B of this question, and let's get that graphic approximation of the area. So we return to this graph. We got this polygon, and now let's make use of this. We can take this polygon and pick up the context menu, go to measurement, and get its area. Alright, and this area will serve as our claimed approximate area of this region, and let me label that as such. Put some text in here. So approximate more text area is, and we have that 8.08 square units. Okay, so let's go ahead to the summary page and actually explain what we've done here. This is the main page, part B. So we could say that a graphic approximation can be obtained by using an approximating polygon. The area of this polygon is about, okay, we don't need 3 digits here, we'll still call it 8.1 square units. And I suppose we can say here, C, page 3. Alright. Part C, provide a calculus calculation which yields a decimal approximation, 5 significant digits, of the area of the region. Okay, in calculating an area in calculus, in rectangular coordinates, basic idea is to slice up that region into thin rectangles and then sum the areas of those thin rectangles. So the question is, do we want thin vertical rectangles or thin horizontal rectangles? And we need to formulate the area of each of these little rectangles to set up our integral. Okay, we do this visually. First, let's take a look at slicing up this region with thin vertical rectangles and see if it looks like a good strategy. Okay, we see that we will be able to sum the areas of the thin vertical rectangles by using a single integral. The reason is that all the rectangles have the same general height formulation. Here's why. First, notice the top of each rectangle is passing through the F2 graph. Secondly, notice that the bottom of every rectangle is passing through the F1 graph. Let's next focus on a single thin vertical rectangle and informally formulate its area. The area of a rectangle is height times width. The height of each thin vertical rectangle will be its upper y coordinate, f2 of x, minus its lower y coordinate, f1 of x. The width of each of the thin vertical rectangles will be an infinitesimal change in x, dx. So now we know what to sum up. The remaining issue is where to begin and end the sum. So where do those rectangle widths dx begin and where do they end? Well, the dx begins at the leftmost x-coordinate, and that would be the x-coordinate corresponding to the leftmost intersection point, for which we presently have a 3 significant digit approximation. And those dx's proceed to the right until we get to the x-coordinate of that rightmost point of intersection. And we presently do have a 3 significant digit decimal number for that. Of course, we'll need to improve, but that's the basic idea. Alright, let's try to get some fairly accurate limits of integration, and let's return to our graph here where we pointed out we do have these x-coordinates sitting here. Alright, well, this may display 3 floating digits, but behind the scenes there are 14 decimal digits in the Nspire. So to get a whole access to those and not have any have minimal and intermediate error in our calculation, we can go here, get a context menu, pick up store, and well, let's see, the favorite letter for a left-hand limit of integration is A, but the Nspire likes us to, or suggests that we not use single letters as variables, so I'll try to keep good habits and call it A1. And then because I am using this as a decimal approximation, I will suffix it with an A, so it's like A1 approximate, and enter. Okay, there's a left-hand limit of integration, and over here let's get this quantity here. Accessible is a more accurate version. Go to store, and B is the usual right-hand limit of integration. We'll call it B1 to follow Nspire's suggested variable naming and suffix it with an A because it's only a decimal approximation, although it's 14 decimal places of precision, not too shabby. Okay, now we have that in place. We're ready to go to the notes page, I suppose, and go ahead with our calculus calculation that we've been discussing here. A calculus computation of area can be formulated by an integral which sums thin vertical rectangles. Alright, so here we go. Area equals, let's go here to the menu and calculations and calculus and integral. There we are. Now our A1A there, tab, B1A, tab. We talked about this. The height of each rectangle is the F2 of X minus F1 of X. Tab dx. Remember the thickness there. Okay, here's our sum of thin vertical rectangles. Hit enter. Alright, well, now we actually have 4 significant digits because the float 5 has realized that the next digit there is 0 and it's choosing not to put anything. So float digits and significant digits are not exactly the same thing. We can compensate for that a bit here. We can put in our own 0. Little other thing here. Let's come back here. Let's format this box a little bit. Instead of that little arrow, I think it looks nicer to have an equal to sign there. And the units of measure here, although they're not really existing, maybe it's just a good habit to keep writing things like square units when you do an area, so you have good habits and you will never forget units of measure when you're doing a real problem. It's time to go to part D, which is the assessment of correctness here. Well, let's look back here. You got that calculus calculation 8.26. What was the graphic approximation? 8.1. Okay, this is very reassuring. So let's discuss that here. The graphic approximation was 8.1, while the calculus calculation was about 8.3. These results are, well, let's see, it's very close. 0.8 would be 10%, within 0.4 of each other would be about 5%. So just something that's not exaggerating at all would be to say that these results are within 5% of each other and thus consistent. Thus, it is likely that the solutions B and C are correct. Part E, if able, obtain an exact value for the area of the region. Okay, let's look back here at what we did in part C, and we had an definite integral with those limits of integration, A1A and B1A. Well, they were approximations, right? If we go back and look where we got those, we pull them off the graph. And the graph application is great and fast. However, these numbers here are decimal point containing numbers, and that's going to force the integral to be a decimal point number as well. All right. Well, the first thing we need to do is obtain these limits of integration exactly and make sure they also have no decimal points in them. Will we be able to do that? Maybe we should take a look at the formulations of F1 and F2. You notice that there are no decimal point containing numbers in either formulation. Okay, we're ready to try for an exact solution for these points of intersection, but to do so we need to go to a calculator application. So let's do a control add page, add calculator, and let's go with a solve f1 of x equal to f2 of x. X has the variable, enter. Great. We indeed have found exact values for those limits of integration. Now let's get a hold of them. So I'll go back up here. Let me cursor left. Now when the solve function goes to work, it provides solutions in ascending order. So this first number must be the left limit of integration. Now I'm going to push shift and arrow right to highlight it, and then I'll hit enter to bring it to the new line, and I want to store that. Control store to. Alright, now this is exact, so I'll call this one A1. Remember the decimal approximation version? I chose A1A to remind me it was an approximation. Now I have exact limit of integration. I call it just A1 and enter. Okay, similarly, that second limit of integration, shift key arrow left in this case, I'm going to go enter to paste that onto the new line, and then control store to B1. Put that one in B1. Enter. Alright, probably time to go to the main first page and start recording our results, as well as hope maybe succeeding on getting the exact area. Okay, enter. E. For an exact area, we first need exact and no decimal point containing limits of integration. Okay, we succeeded with this, and we can refer to page 4. Okay, there. Now, we sort of cross our fingers as we now attempt. Let's go to the menu, Calculations, Calculus, Integral. Okay, lower limit, A1, tab, upper limit, B1, tab. Okay, height of those rectangles again. That's the F2 of x minus F1 of x, tab dx, the width of each rectangle. We cross our fingers as we hit enter. Okay, nice. We did get an exact area from this. Let me attach the square units And let me get the properties of this box so that that little symbol there is an equals to. Okay, great there. And you know, there's one more thing that it could be worrisome. It just doesn't feel entirely confident until we make sure that this radical containing exact number is numerically the same as our decimal calculation of part B. So let's go do that. We could write a new sentence here. And here I want to go up to this, I want to grab this number here. So I'll go and shift, arrow left. I'll go Control C to copy that. Then come down here and now Control V. This pastes it into a math box. Now I will context menu and go to actions and have this approximated. Oh, good. All right. You know what? That's the same as our part B answer. This is just what we wanted to see. Let's just fix up this box a little bit with that little symbol there being an approximately equals to. There we are. And then we can kind of finish the sentence here, which is consistent with the decimal result of part B. Okay, very nice. Good job.